Welcome back to the Deep Dive. We're the show that takes those dense enterprise strategy docs, rips out all the fluff and tries to get right to the actionable stuff.
Yeah, cut right to the chase.
Exactly. And today, we've got a big one, a really big one, the Enterprise Cloud Modernization Blueprint.
Oh, this is a fantastic find.
Well,
Seriously, we're not talking about some high-level, glossy marketing deck here.
no PowerPoints full of buzzwords.
None of that. This is essentially a 3-year strategic roadmap, and it's been put together by an expert architect, someone really in the trenches, for a heavily regulated organization.
Okay, regulated. That always adds layers, doesn't it?
Layers and layers, yeah. Think finance, healthcare, that kind of thing. And this place, they've got mountains of legacy Windows stuff, Hyper-V workloads everywhere.
The classic scenario.
The classic headache, yeah. And the goal is to securely shift all of that into a dual cloud environment. They're specifically targeting Azure and AWS.
Right, dual cloud and regulated and legacy Windows. That's complexity dialed up to 11, isn't it?
Absolutely. You've got governance across 2 major hyperscalers. You got to somehow integrate maybe creaking old Active Directory setups and meet all those strict non-negotiable compliance rules.
So the source material we're digging into today.
It's actually an architect-level scenario interview transcript. Really detailed. It lays out this whole plan, connecting the dots between the overall strategy, the nuts and bolts of security, and, importantly, site reliability engineering, SRE. It pulls it all into one, coherent vision.
It sounds like the kind of document every CISO, every CTO wishes someone would just hand them.
Pretty much, yeah. It's the blueprint.
Okay. So our mission today, for you listening, is simple. We want to give you the shortcut.
The cheat sheet.
The cheat sheet, exactly. We're going to synthesize this whole complex strategy. The idea is you walk away understanding the critical parts, the must-dos, things like how does zero trust security actually work in practice here? How do you implement FinOps so people are actually accountable for costs? And what are the essential architectural steps you just can't skip?
And crucially, how they all interact. Because they do. Security decisions impact cost, architectural choices impact reliability. It's all connected.
We're skipping the philosophy, jumping straight into the concrete stuff, the deliverables.
Right. And if you're doing modernization at this kind of scale, you can't boil the ocean. You can't do it all at once.
No way.
So this architect, they proposed a really clear, phased approach. And the key thing, especially early on, the goal is survival, not necessarily optimization straight out of the gate.
Okay, let's dig into that roadmap. I thought it was brilliant, partly because it's just so honest about the priorities. Year 1 is literally called stabilize and secure.
Exactly.
It's not save money instantly or launch shiny new serverless apps. It's, like you said, survival. Stop the bleeding, get a reliable, secure baseline in place.
Precisely. And the steps here, the foundational one, they are absolutely non-negotiable. Priority number 1, right off the bat, implement immutable backups. Immediately.
Your ransomware insurance policy.
That's exactly what it is. Use tech, like Vault Lock, immutable storage. Basically, you make it so that even if an attacker gets full admin control, they cannot delete or mess with your recovery data. It's fundamental.
That's the critical defense layer. Okay, what comes next in year 1? It feels like a lot of operational hygiene, the stuff that often gets glossed over when everyone's rushing to the cloud.
It is.
Yeah.
And it's vital. The year 1 deliverables, they defined sound basic, but for a regulated place, they're essential. Things like making absolutely sure patching and antivirus, AV compliance, is sorted across the entire legacy estate, not just the new stuff.
All the old Windows Server 2008 boxes hiding in corners.
Hopefully not 2008 anymore, but yeah, all of it. And critically, building an accurate configuration management database, a CMDB.
Okay, let's pause there. The CMDB. Why is just knowing what you have such a foundational headache for year 1?
Because without it, how can you possibly scope the migration accurately? How do you right-size the services you're moving? How do you even know what policies to apply where? You just can't. The CMDB has to become the single source of truth, and that feeds directly into the next year 1 piece.
Which is?
Setting up the basic landing zones in both Azure and AWS.
Yeah.
But not just empty containers. They need to have strict, policy-driven guardrails from day 1, things that prevent insecure configurations right from the start.
Makes sense. Get the safe sandbox built first. And year 1 also forces that really hard strategic conversation, right? The application portfolio assessment.
Oh, yeah. The 6 Rs. You absolutely have to look at every single workload, every application, and decide its fate.
Let's quickly list them. Rehost.
Rehost, which is your basic lift and shift. Refactor, meaning you change the code structure, maybe modernize it a bit.
Yeah.
Replatform, like moving from a self-managed database VM to a pious database service,
Repurchase?
moving to a SaaS alternative if one exists, retain, meaning you consciously decide to keep it on-prem for now, or retire it altogether, just switch it off.
Yep. And that assessment, that categorization, that really dictates the next 2 years, doesn't it?
It dictates probably 80% of the cost and the effort. If you skip this step or do it badly, you just end up lifting and shifting a whole load of complexity and cost into the cloud that you maybe didn't need to. You're just moving the mess.
Which brings us nicely into year 2. Migrate and replatform. Okay, so this is where the heavy lifting, the actual moving, starts happening.
Is the execution phase,
Yeah.
But it's also about shifting how you operate. You're obviously using the native migration tools. Azure Migrate is great for Hyper-V. AWS has its migration services. But the really strategic move in year 2 is actively transitioning workloads to managed services wherever it makes sense.
Give us an example.
Think about the operational difference between managing, patching, backing up a Windows VM running SQL Server versus using Azure SQL Database PADS or AWS RDS, or maybe replacing an old on-prem file server cluster with Azure Files or AWS FSx. That immediate drop in operational overhead, less patching, less management, that's a key payoff you target in year 2.
Okay, so reducing the toil. And year 2 is also where infrastructure as code IAC stops being an experiment and becomes the standard, right, across both clouds.
Absolutely mandatory. Terraform modules become the required way to provision anything significant. And alongside that, you absolutely must deploy a proper, standardized observability baseline.
And the blueprint was specific here. It mandated OpenTelemetry.
It did. And that's a strategic choice, not just a tech preference.
Why OpenTelemetry specifically? Why not just rely on, say, Azure Monitor for Azure stuff and AWS CloudWatch for AWS stuff?
Yeah, good question. It boils down to avoiding vendor lock-in and achieving standardization. In a dual cloud setup like this, if you only use the native tools, you end up with monitoring data in 2 completely separate silos. It's hard to get a single view.
Right.
OpenTelemetry gives you a unified model, a common language for logs, metrics, and traces. It ensures that all your services, whether they're running on Azure or AWS, or even still on-prem, emit telemetry data in the same way. This is absolutely critical for doing effective, centralized SRE analysis later on. You need that unified view.
That makes a lot of sense. Avoid the silos. Okay, so that takes us to year 3. Optimize and evolve. This sounds like where you finally start reaping the bigger cloud benefits, the optimization, the acceleration.
This is the payoff phase, yeah. Now you can really start driving more advanced capabilities. Things like implementing auto-scaling properly, maybe moving towards more event-driven architectures where it fits, adopting serverless components, Lambda, Azure functions for suitable workloads, like replacing old scheduled task scripts.
Getting more efficient, more cloud native. And the architect was really insistent here on formally enforcing SRE practices. We're talking defining clear service level objectives, SLOs, and establishing error budgets.
Yes. This is the mechanism that actually guarantees continuous improvement and reliability. It's not just hoping things get better. An SLO is your target, say, 99.9% uptime for a critical service.
Okay.
The error budget is basically the amount of acceptable failure or downtime you can have and still meet that target over a given period, say, a month.
And the teeth come in when you burn through that budget.
Exactly. If a team exhausts their error budget for a service, the rule is they must prioritize work that improves reliability over shipping new features. It forces a focus on stability. And honestly, this is as much a cultural shift for development teams as it is a technical one.
I can imagine. And the final really advanced piece in year 3 sounded like automating disaster recovery, DR, workflows, and this sounds scary, conducting critical, controlled chaos drills.
Yeah, chaos engineering. You have to actually intentionally try to break things in a controlled way to really validate your resilience. Otherwise, your DR plan is just a document. It's just theory.
You don't know if it works until you test it under pressure.
Precisely. And crucially, throughout all 3 of these years, the progress can't just be technical milestones. It has to be quantifiable in business terms. You've got to constantly tie all this massive technical effort back to actual business metrics.
Not just uptime improved by 0.1%.
No. It needs to be reduction in downtime cost us X dollars less this quarter, or our security posture score improved by Y points, or even the cost per transaction for this service went down by Z%. If you can't demonstrate the value in language the business understands, you'll lose momentum. The funding could dry up. Hashtag tag 1.2. Defining the target operating model, TOM.
Okay, so that's the technical roadmap. But as you said, that's only half the story, maybe less. This kind of massive migration, it just fails without fundamental changes to how the organization itself works. The target operating model that Thomas Yu described here sounds like a pretty huge shift.
It's a massive shift. The
Yeah.
primary change, the biggest one, is moving away from those traditional siloed teams, the separate infrastructure team, the apps team, the security team, the network team.
Everyone in their own swim lane.
Exactly. And moving towards product-aligned teams. The idea is the team that owns a business feature, they own it end-to-end. They own the code, sure, but they also own its deployment pipeline, its security profile, its reliability and production, and yes, even its cost.
That level of end-to-end ownership sounds great on a slide, but doesn't that create huge friction in practice? I mean, historically, infrastructure was centralized partly to save money and ensure things were done consistently, right? Doesn't giving every team control lead to chaos or massive cost overruns?
That's the potential pitfall, absolutely. And that's precisely where the dedicated platform engineering team comes in. They are the crucial enablers in this model. They don't manage every single workload. That's not their job. Their job is to build the tools, the standards, the shared services for everyone else.
So their role is establishing those, what was the phrase? The golden paths.
Yes, the golden paths, that's exactly it. These are the pre-approved, compliant, secure, and well-documented ways that developers must provision and consume cloud services.
So the platform team builds, say, the standard approved Terraform module for deploying a database with all the security controls baked in.
It's exactly. Or the standard CI/CD pipeline template, the central logging collectors, the policy enforcement tools. They provide the paved road. This ensures the product teams can move fast, they have autonomy, but they do it within safe, standardized guardrails. They don't have to constantly reinvent basic infrastructure or security practices.
Okay, that makes sense. And operationally, the change sounds pretty radical too. Central security, for instance, moving away from being the team that just says no at the end of the process.
Yeah, the traditional gatekeeper model.
And moving towards operating via policy as code. What does that actually mean day to day?
It's a huge shift in mindset and tooling. Instead of relying solely on manual security reviews before deployment, compliance checks are embedded directly into the CI/CD pipelines. They use configuration analysis tools, policy engines.
So the pipeline itself checks if the deployment meets security standards.
Right, before it even gets close to production. And this means the operations teams, their world changes completely too. They transition away from being reactive, working off tickets, please provision me a VM, please open this firewall port.
Ticket queues stretching into infinity.
Exactly, to being proactive, working through pipeline-based workflows. Pretty much all changes, whether it's deploying new code or patching an existing system, should be driven through Git, managed by code, and executed via automated pipelines. Less manual intervention, more automation.
Okay. And another piece woven right into this new operating model is FinOps, financial operations. This seemed non-negotiable in the blueprint, especially for controlling those cloud costs.
Absolutely non-negotiable. The expert was really clear. Budget ownership must be mapped directly to those product teams. They need accountability. If they own the feature, they own its running cost too, not just the initial build cost.
That's that trade-off you mentioned earlier, isn't it? Giving teams budget ownership makes them accountable, which is good. But it could also maybe create a perverse incentive, like they might avoid using a more expensive but much better, more reliable managed service because they're worried about their budget line item.
That's a real risk, yeah. And that's precisely why the central FinOps team, or function, is so critical.
Yeah.
They aren't just tracking spend. They need to provide clear visibility and analysis, showback reports, cost modeling. They need to help teams understand the value proposition.
So they can demonstrate the ROI.
Exactly. Show that, yes, the Spanish database costs more per hour than a VM, but look, it saves X hours of operational toil, it includes automated backups and patching, it scales better. Shifting the conversation from just why is this costing so much to what business value are we actually getting for this spend? It needs that partnership.
Got it. And finally, just to wrap up the Tom, in this really complex hybrid multi-cloud world, clarity of ownership seems absolutely paramount.
Oh, absolutely critical. The architect really hammered this point. You must define a clear ROCI matrix. Who is responsible, who's accountable, who needs to be consulted, and who just needs to be informed.
The classic RCI.
The classic, yeah, but often overlooked. You need it for all the critical cross-cutting domains, especially things like identity management, overall network topology and security, central security policies, and data stewardship, who owns what data. Without that crystal clear demarcation of duties, especially in a dual cloud setup, operations just dissolve into confusion and finger-pointing really, really fast when something goes wrong.
Yeah, avoiding the "it wasn't my team's fault" game.
Exactly that.
Okay, let's pivot specifically to security now. It's the bedrock, right? Especially for a regulated company. How do you actually go about implementing zero trust across this kind of sprawling environment, hybrid, multi-cloud, where the fundamental assumption has to be assume breach?
Mhm.
Where do you start?
It absolutely starts with identity. The core strategy, the guiding principle for zero trust here is identity first. Everything hinges on verifying the identity.
Okay, so practically, what does that mean?
It means immediate identity federation is step one. You need a central place to manage identities. In this blueprint, they specified using Entra ID, what used to be Azure AD is the primary source, or AWS Identity Center if you're more AWS-centric, and then mandatory multi-factor authentication, MFA. Mandatory across every single access path, no exceptions. Doesn't matter if the user is on-prem, accessing Azure, hitting an AWS service, or logging into a SaaS app, MFA everywhere.
Verify the user strongly, but zero trust isn't just about the user, right? It's also the device they're using.
Correct. You can't just trust the user. You have to verify the health and compliance of the device trying to access the resource before you grant access. Is it patched? Is the endpoint protection running? Is it managed by the company?
Okay, user identity, device health. What about administrators? People with the keys to the kingdom.
For them, access must be just in time, or JIT. Standing privileged access is just too dangerous.
So using tools like PM in Azure or JEA.
Exactly. PM is privileged identity management. JEA is just enough administration, more for specific tasks on Windows.
Let's quickly clarify for listeners who might have heard those acronyms but maybe haven't rolled them out yet. What's the practical difference JIT makes for an admin's daily life? How does it change things?
It means your admin account doesn't actually have powerful permissions by default. To do something privileged, like changing a firewall rule or managing a database, you have to explicitly request elevation. You usually have to provide a justification, maybe it needs approval, and crucially, the access is granted only for a limited time, say 1 hour.
And then it's automatically revoked.
Automatically revoked. It dramatically shrinks the window of opportunity for an attacker if they manage to compromise an admin's account or session. Minimizing standing privileges is key.
Okay, so identity and device are locked down. What about the network? We hear a lot about microsegmentation and zero trust. Is it about getting rid of the big perimeter firewall?
It's less about getting rid of it entirely, more about not relying on it as your only defense. The focus shifts inwards. You rely heavily on the native cloud controls for segmentation within your environment.
Like NSGs in Azure, security groups in AWS.
Yes, exactly. Network security groups in Azure, security groups coupled with careful VPC segmentation in AWS. But crucially, the blueprint also mandated enforcing host-level firewalls on the VMs themselves.
So defense in depth, network rules plus OS rules.
Precisely. If one layer fails, maybe a network rule is misconfigured, the host firewall still provides containment. An attacker can't just jump freely between machines even if they get onto one segment.
And the architect made a really strong point, a mandate really, about passive services, things like databases, storage accounts, messaging queues.
Yes, this was non-negotiable in the plan. All PaaS resources must use private endpoints or private link equivalents.
Meaning they have no public IP address.
Exactly. They are removed entirely from the public internet. Access is only possible from approved private networks within your own VNet or VPC, tunneled directly to the service endpoint. This is a critical security guardrail. It might add a little bit of network configuration complexity up front, but the security game is massive.
So the overall guardrail is pretty clear. Minimize public exposure, especially for admin interfaces and POLX. But even with internal segmentation, you still need to watch the traffic flows, right? Continuous verification.
Absolutely. Zero Trust isn't a one-time setup. It's continuous verification. That's where comprehensive monitoring comes in. The strategy requires inspecting all outbound traffic egress inspection, primarily to prevent data exfiltration. You need to know what's leaving your network.
And how do you monitor all this effectively?
You layer your monitoring. You absolutely need a SIEM security information and event management system to correlate logs from everywhere. But critically, the blueprint also calls for UEBA user and entity behavior analytics.
UEBA, what's that looking for?
It's looking for anomalies, patterns of behavior that deviate from the norm for a specific user or a specific service account, things that traditional signature-based tools might miss. Like, why is this user suddenly accessing data they never touch? Or why is this server trying to connect to a weird IP address? UEBA helps spot compromised accounts or insider threats.
Okay, so strong identity, device compliance, JIT, microsegmentation, private policy, continuous monitoring with SIEM and UEBA. The ultimate goal then is
The ultimate goal is simple in concept, hard in execution. Enforce, deny by default, everywhere you possibly can, driven by policy as code. Access is denied unless explicitly permitted based on verified identity, device state, and context. Take 2.2, unifying identity and privileged access.
Let's drill down a bit more on that identity piece, because it often becomes a real pain point, right? You've got legacy Windows AD, you've got Azure, you've got AWS, you've probably got dozens of SaaS apps. How do you unify identity across all that? What's the anchor?
You need a single source of truth for identity if possible. In this enterprise blueprint, Entra ID, again, formerly Azure AD, was specified as the primary identity provider, the IDP. That's the anchor. It then federates down to AWS, typically via AWS IAM Identity Center, so users log in with their familiar corporate credentials. And for SaaS apps, you use standard protocols like SAML or Scheme System for cross-domain identity management or JIT provisioning where possible. The goal is one place to manage user accounts, group memberships, and enforce access policies. One place to audit from.
Makes sense. Central control. And for enforcing least privilege for those user accounts, especially admins, PIM is mandated for all privileged roles. We covered that. But what about applications? They need identities too, right? How do we stop using static secrets, API keys stored in config files?
That was a massive focus in the blueprint. The reliance on static, long-lived credentials for applications is explicitly forbidden. It's just too risky. They mandate the use of workload identities. Meaning using things like managed identities in Azure or IRSA IAM roles for service accounts in AWS, particularly for Kubernetes workloads.
Okay, IRSA and AWS for K8s. Can you quickly explain what that achieves for listeners running containers?
Yeah, sure. IRSA basically lets a specific service account inside your Kubernetes cluster assume an AWS IAM role directly. So the application running in a pod gets temporary, short-lived AWS credentials dynamically based on the role you assign to its service account.
So no need to mount secret files with AWS keys.
Exactly. The pod never touches or stores static AWS keys. It dramatically lowers the risk of those credentials leaking out through code vulnerabilities, logs, or configuration mistakes. It's a much more secure way for apps to talk to cloud services.
Big improvement. And for the really, really sensitive human operations, like managing the domain controllers or the core PKI infrastructure, the architect mandated something called a PAW, a Privileged Access Workstation.
Yes. A PAW is essentially a dedicated, heavily secured, hardened machine. Often it's a virtual desktop, locked down tight. It's only used for performing highly sensitive administrative tasks.
So you don't manage your core infrastructure from the same laptop you use for email and web browsing.
Exactly that.
Yeah.
It enforces separation. It ensures the environment where you're performing those critical high-impact tasks is isolated from the general user environment, which is much more likely to encounter malware or phishing attacks. It drastically reduces the risk of credential theft targeting high-privilege accounts.
Okay. And finally, on identity governance, making sure people only have the access they need and only for as long as they need it.
Automation is key here. The strategy requires automating quarterly access reviews for all privileged roles systematically.
So the system prompts the owner of a resource or role.
Yes. The owner gets a notification. Does this person still need this level of access? They have to actively attest, reapprove it. If they don't respond or if they say no, the access is automatically revoked by the system. It stops privilege creep and ensures access is regularly validated rather than relying on manual spreadsheets and hope. Automation drives that compliance. Hashtag 2.3 ransomware resilience and PKI design.
Let's talk about the elephant in every CISO's room: ransomware. Resilience today clearly means more than just having backups, even immutable ones. What are the critical layers beyond those immutable backups, according to this blueprint?
Right. Immutable backups are the foundation, your recovery safety net. But you need layers to prevent the attack succeeding in the first place, or limit its blast radius. The strategy layered on top, the network segmentation we discussed, the JIT admin access to limit credential abuse, and critically, application whitelisting.
And the blueprint specifically called out WDAC Windows Defender Application Control.
It did.
Why WDAC specifically? What's the advantage?
It represents a fundamental shift from reactive security to proactive security. Traditional antivirus mostly relies on blacklisting, recognizing known bad files by their signatures.
Trying to keep up with the bad guys.
Yeah, a constant cat and mouse game. WDAC, or application whitelisting in general, flips that. It works on the principle of whitelisting. Only applications, scripts, binaries that have been explicitly approved and signed off by the security team are allowed to execute on the endpoints, especially servers.
So if it's not on the approved list, it doesn't run, period.
Period. This is incredibly effective at preventing the execution of almost all novel zero-day ransomware variants because they simply won't be on the whitelist. It significantly raises the bar for attackers.
Okay. And those administrative pathways, they need to be really isolated, right? To stop attackers moving laterally if they do get a foothold?
Exactly. That ties back to the PAW concept in JIT. The credentials used by privileged admins should never touch a regular production workload server directly if you can possibly avoid it. You use jump boxes, bastion hosts, PAWS beers. This isolation is what breaks the kill chain of many ransomware attacks. Often they compromise an admin's regular machine or account and then use those cached or stolen credentials to spread rapidly through the network. Isolation prevents that lateral movement.
Makes sense. And for recovery, if the worst does happen, the blueprint used the phrase clean room rebuilds. What does that entail?
It means you absolutely do not trust the existing, potentially compromised environment after a major incident like ransomware. You don't just restore files back onto the infected servers. You build a brand new, completely separate, clean network segment, untainted infrastructure.
Start from scratch.
Start from scratch. You restore your verified immutable backups onto that clean infrastructure. You revalidate everything. Test the functionality thoroughly before you even think about reconnecting it or migrating users back. And the architect mandated building comprehensive step-by-step recovery runbooks for this, and crucially, conducting periodic restore validation exercises to prove those runbooks actually work in practice, not just on paper.
Testing the plan regularly. Okay, let's shift gears slightly to another unsung hero, or maybe sometimes villain, of enterprise security, the public key infrastructure, or PKI, certificates. With the big push towards mutual TLS, secure LDAP, code signing, a robust PKI seems essential for this modernization.
Absolutely essential. And often, legacy PKI setups are just not fit for purpose for the demands of modern cloud and security practices. So redesign is often mandatory.
What's the recommended secure approach?
The standard best practice approach is required here. The secure two-tier PKI hierarchy model.
Explain that quickly.
Okay. You have an offline root certificate authority, or CA. This machine creates the ultimate trust anchor, signs the subordinate CAs, and then it's powered off, disconnected from the network, locked in a vault somewhere. It never touches the live network.
Okay, the root is safe.
Then you have one or more online issuing CAs. These are subordinate to the root. They live on the network, and they are the ones that hourly issue the certificates to end users' servers' devices. This structure means if an online issuing CA somehow gets compromised, you can revoke it, take it offline, and the entire trust chain doesn't collapse because the offline root is still secure and can issue a new, trusted subordinate CA.
Got it. 2 tiers for resilience. What are the practical details that often trip people up when deploying or managing a global PKI like this?
Availability and distribution are huge. The endpoints that clients use to check if a certificate has been revoked, the certificate revocation list, or CRL distribution points, and the online certificate status protocol, or OCSP responders. These must be globally distributed and highly available.
Why is that so critical?
Because if a client, say a web server validating a client certificate, can't reach the CRL or OCSP endpoint to check if the certificate is still valid, the connection might fail. Depending on the configuration, it could cause widespread application outages. People often underestimate the importance of the revocation infrastructure.
So high availability for revocation checking. What else?
The strategy also mandates using relatively short-lived certificates reduces the window of exposure if a key is compromised, and leveraging automated enrollment and renewal processes wherever possible. Using group policy objects, GPO for Windows auto-enrollment, or maybe ACME protocol for non-Windows systems, to reduce the manual burden and human error involved in certificate lifecycle management.
And for the really sensitive keys, like code signing certificates or the keys for the issuing CAs themselves.
Hardware. Mandatory use of hardware-backed key storage. That means using hardware security modules, HSMs, or potentially TPMs, trusted platform modules, on servers where appropriate. You absolutely cannot leave the private keys that sign your company's critical business code or the keys that underpin your entire PKI trust structure, sitting unprotected in software files on a standard server VM that could be easily compromised or backed up insecurely. Hardware protection is a must for high-assurance keys.
All right, let's wade into the network swamp now. This always gets complicated fast. We've got on-prem data centers, we've got an Azure hub and spoke setup, we've got AWS with multiple VPCs, and they all need to talk to each other securely or reliably, performantly, and ideally without costing a fortune.
Yeah, this is often the operational minefield in big migrations. The connectivity strategy laid out here is pretty rigorous, as it needs to be.
So on-prem connecting to the cloud.
On-prem connects securely into Azure, primarily via ExpressRoute. That gives you a private, dedicated, high-bandwidth connection bypassing the public internet.
Okay. And that Azure Hub VNet, it's not just a simple router, is it?
No, absolutely not. It's the central point of control. It hosts the main firewall or network virtual appliance and VA for inspecting traffic. It hosts central DNS forwarders, maybe your Active Directory domain controllers for the cloud, and the Bastion service for secure, agentless administrative access into the spoke VNets where the workloads live.
Hub and spoke. Got it. Now, connecting the two clouds, Azure and AWS, how do you bridge that gap securely and effectively?
For enterprise-grade, high-bandwidth needs between the two, the preferred method specified is using Azure ExpressRoute paired with AWS Direct Connect, interconnected via Partner Exchange, or maybe cloud-native options like ExpressRoute Global Reach connecting to a Direct Connect gateway. These give you premium, dedicated private connections between the hyperscalers' own backbones.
So, avoiding the public internet again, what about simpler VPNs?
Standard IPsec VPN tunnels over the internet are really only positioned as a fallback. Maybe for lower bandwidth requirements, less latency-sensitive traffic, or perhaps as a cost-saving measure if the premium connections aren't justified for a particular link. But for core interconnectivity, it's ExpressRoute and Direct Connect.
Okay. And within AWS itself, the recommendation is to use a transit gateway.
Yes, for managing routing at scale within AWS. A transit gateway acts as a central cloud router. You connect all your VPCs and your direct connection to the TGW, and it handles the routing between them. It avoids complex mesh peering between VPCs and simplifies management significantly as you grow.
Sounds cleaner. But the real nightmare fuel in hybrid multi-cloud networking often seems to be IP addresses and DNS. Right?
Oh, absolutely. This is where so many modernization efforts stumble or crash and burn completely. The blueprint is adamant. You need a shared, centrally managed IP address management tool or system. And you need meticulous planning of your CIDR block allocations across on-prem, Azure, and AWS before you start deploying things.
Why is that pre-planning so critical?
Because if you end up with overlapping IP address ranges, say, your main Azure VNet uses the same 10.1.0.016 range as a critical VPC in AWS, they simply cannot communicate directly. Routing becomes a nightmare, requiring complex NATing or just failing completely. You have to plan the address space carefully up front to avoid painting yourself into a corner.
Avoid the overlap at all costs. And DNS, making sure everything can find everything else by name.
Equally critical and needs explicit design. You need DNS forwarding set up correctly between your different environments. Requests originating in Azure need to be able to resolve names hosted in AWS Route 53 and vice versa. Maybe you have Azure DNS forwarders talking to Route 53 resolver endpoints and potentially also talking back to your on-prem DNS servers.
Especially if Active Directory is involved.
Exactly. AD relies heavily on DNS. Every resource, regardless of where it lives, on-prem, Azure VM, AWS EC2 instance, pair mesh service, needs to be able to resolve internal names correctly and reliably. Seamless DNS resolution is really the invisible bridge that makes the entire hybrid multi-cloud environment feel like one unified network, rather than a collection of disconnected islands. Hashtag 3.2 handling data transfer costs and resilience.
That network complexity often leads directly to another major headache: runaway data transfer costs, especially those sneaky inter-AZ costs, data moving between availability zones within the same region, or just massive egress charges for data leaving the cloud. The blueprint had some specific tactics for tackling these silent budget killers, right?
It did. These costs can really bite you if you're not careful. For applications that are really chatty, maybe multi-tiered apps or microservices constantly talking to each other, the primary tactic is strict collocation.
Meaning keep them close together.
Keep them in the same availability zone. If the front-end server, the API layer, and the database are all in AZ1, the traffic between them stays within that zone. Inter-AZ traffic usually has a cost, while intra-AZ traffic is often free or much cheaper.
Okay, but what about high availability? Don't you need things in multiple AZs?
You do for resilience, yes.
Yeah.
So you might deploy the whole stack in AZ1 and AZ2 and use a load balancer. Or maybe you keep the primary compute in AZ1 but use synchronous database replication to AZ2 for HA. The key is minimizing the constant high-volume chatter across AZ boundaries. The core application traffic should ideally stay local within one AZ during normal operation.
Got it. Minimize the cross-AZ chatter. What else? Can you optimize the data itself?
Absolutely. Two main things there. Aggressive payload compression wherever possible, especially for large data transfers, and adding caching layers strategically.
How does caching help with transfer costs?
If you can cache frequently requested API responses, database queries, or static content closer to the consumer, maybe in the same AZ or even at the edge, you avoid repeatedly fetching that data across the network. Fewer fetches mean less data transfer, which means lower costs and often better performance too.
Makes sense. Okay, what about broader disaster recovery, maybe across different regions? That sounds like it could get incredibly expensive if you're replicating everything everywhere constantly.
It can. Full synchronous replication across regions, aiming for zero data loss, is technically possible for some things, but it's usually extremely expensive and often introduces unacceptable latency for the primary application.
So what's the realistic approach?
The architects strongly advocated for asynchronous replication, but carefully tailored to the actual business requirements. You need to have honest conversations about the RPO recovery point objective, how much data can we afford to lose, and the RTO recovery time objective, how quickly do we need to be back up for each specific business-critical data set.
Don't apply a one-size-fits-all DR strategy.
Exactly. If the business can genuinely tolerate, say, 15 minutes of data loss for a particular system, an RPO of 15 minutes, then you absolutely should not be paying the premium for near-zero data loss synchronous replication. You design and pay for the level of resilience the business actually needs and is willing to fund. You tailor the recovery goal to the business's appetite for risk and cost.
Match the tech to the need.
Mm.
Okay. And one last area notorious for high data transfer costs: massive analytics workloads. Data warehouses, data lakes, pulling huge data sets out can rack up enormous egress bills.
Yeah, analytics egress can be a killer. The solution strategy here focuses heavily on keeping the data movement internal to the cloud, or at least minimizing what has to leave.
How do you do that?
First, co-locate the compute your query engines, like Spark clusters or data warehouse nodes, and the storage, your data lake, in the same region, ideally even the same AZ if possible. Second, compress the data heavily in storage. Third, use efficient column storage formats like Parquet or ORC, which allow query engines to read only the specific columns needed, not the whole data set.
Reducing the amount read and transferred.
Exactly. And fourth, crucially, if that processed data needs to be consumed by other internal applications or services, make sure they access it via private endpoints. Don't let the analytics platform just dump results out over a public internet connection if the consumer is also within your secure cloud environment. Keep it on the private fabric. Hashtag tag 3.3 multi-cloud decisions and data residency.
Okay, we've talked a lot about dual cloud, Azure and AWS in this case. But the architect's default preference seemed to be single cloud, if possible, right? For simplicity, for cost control. So when should a large enterprise bite the bullet and embrace the complexity of a true multi-cloud architecture?
Yeah, the default should always be single cloud unless there's a really compelling reason otherwise. Multi-cloud inherently increases operational complexity. You need skills and multiple platforms, you have different APIs, different tools, different security models sometimes. It mandates budgeting for integrating potentially vendor-specific tooling. It just adds overhead.
So what are those compelling reasons that might justify it?
The blueprint outlined a few strong drivers. One is regulatory jurisdiction. Maybe one cloud provider has a specific region or certifications needed for compliance in a country where the other doesn't. Another is critical partner requirements. Maybe a key business partner operates exclusively on one cloud, forcing you to integrate there. Or sometimes it's a deliberate board-level strategic decision to remain vendor agnostic and avoid lock-in, even if it costs more operationally. But it has to be a strong, conscious business driver, not just let's use both because we can.
Okay. And if that decision is made, if multi-cloud is the path forward, what are the absolute must-dos to prevent it descending into chaos?
Standardization through abstraction is key. You have to work hard to hide the underlying cloud differences where possible. This means things like developing shared, well-tested Terraform modules that can provision similar resources, like a Kubernetes cluster, on either Azure or AWS with minimal changes.
Write once, deploy anywhere.ish.
Exactly. It also means using a unified observability stack back to OpenTelemetry again, so you have one way of monitoring across both. And having a deliberate, unified data egress strategy and security policy framework that applies consistently. You absolutely have to accept the inherent increase in operational cost and complexity that multi-cloud brings, and you need to budget for it up front. Don't pretend it's going to be easy or cheap.
Budget for the complexity tax. Got it. And finally, let's touch on data residency. Strict requirements like GDPR in the EU or maybe specific rules in India or other countries about where personal data can be stored and processed. How does this blueprint handle that?
This demands really strict architecturally enforced separation. You absolutely must deploy regional data planes, meaning the actual storage and compute resources that hold and process the sensitive personal data, specifically within the required geographic boundaries for the data subjects of those regions.
So EU citizen data stays on servers within the EU.
Exactly. The central control plane, things like the main management console, central monitoring dashboards, maybe the global identity system that might be allowed to be elsewhere, only if it remains fully compliant with all the relevant data location and access requirements. Often, even parts of the control plane might need regional instances.
And what are the specific technical controls you'd use to enforce this separation and compliance?
Several layers. First, using encryption, but specifically with per-region encryption keys, possibly managed by regional key management services. Second, explicitly restricting or blocking cross-region replication for any datasets containing PII, personally identifiable information. Third, enforcing data loss prevention, DLP policies that understand data sovereignty rules. And fourth, using those high-level governance policies like AWS Service Control Policies, SCPs, or Azure Policy to enforce geographic boundaries.
Can you give an example of what an SCP might do here?
Sure. You could apply an SCP at the organizational root level in AWS that explicitly denies the creation of, say, any S3 bucket or RDS database instance outside of your approved European regions, like Frankfurt or Ireland, for accounts designated to handle EU data. It provides a hard technical enforcement that prevents accidental or malicious data placement in the wrong geography. It's a crucial backstop.
Okay, let's circle back to that enabling force we talked about on the target operating model, the platform engineering team. Their main job is standardization, and the primary way they deliver that, according to the blueprint, is through infrastructure as code, IAC.
Yeah, IEC is fundamental to making this whole thing work at scale. The strategy relies heavily on what they call the golden module approach.
Golden modules, explain that.
The platform engineering team develops, versions, tests, and maintains a central library of reusable Terraform modules, or it could be Bicep, Pulumi, etc., for every standard type of resource teams need to deploy. Think VNets, VPCs, Kubernetes clusters, storage accounts already configured with private endpoints, key vaults, or KMS setups.
So developers aren't writing Terraform from scratch every time.
Exactly. They consume these pre-built, blessed modules. And critically, these golden modules have the organization's security standards, compliance requirements, tagging policies, and baseline monitoring configurations already baked right into them.
So when a product team uses the Golden module to provision a database, they're getting a compliant, monitored database by default.
That's the goal. It makes the easy path the right path. But you still need enforcement. Governance needs to happen before anything gets deployed, not just cleaning up afterwards. And that's where policy checks within the CI/CD pipeline come in, using tools like OPA Open Policy Agent or Comtest.
Okay, OPA and Comtest, what are they actually checking inside the pipeline? What are they looking for?
They are essentially running policy as code against the proposed infrastructure plan, the Terraform plan output before it gets applied. They're verifying things based on rules defined by security and platform teams. Rules like, does this new storage account configuration have encryption enabled? Or does this proposed virtual machine have the mandatory cost center tag? Or maybe, is this network security group rule attempting to expose RDP or SSH to the entire internet?
So it catches policy violations before they happen.
Exactly. It shifts compliance left into the development workflow. And that workflow itself needs to be mandatory and controlled. The blueprint specified the standard Terraform plan first, which shows what changes will be made. That plan then requires an approval step, maybe automated checks, plus a human review for critical changes. And only then does the pipeline execute the Terraform apply to actually make the changes.
Plan, approve, apply, discipline.
Discipline is the word. And it also includes robust drift detection and remediation. The system needs to constantly check if the deployed reality matches the code definition in Git. If someone goes and manually changes a firewall rule in a server, the IEC system should flag that drift, alert on it, and ideally have an automated way to revert it back to the desired state defined in code. This minimizes configuration drift and reliance on those emergency break glass mechanisms, which should be reserved for true, documented emergencies only. Hashtag tag 4.2 GitOps and configuration management.
That leads nicely into GitOps, which is really the operational model for managing modern infrastructure and applications defined in code. The blueprint emphasized clear structure in your code repositories, right?
Yeah, clear separation is important. The architect mandated distinct repositories. One set for the infrastructure definitions themselves, the Terraform, the core network stuff, and separate repositories for the application code and its deployment configuration. like Kubernetes manifests, Helm charts, application settings.
Why the separation?
It allows for different life cycles, different review processes, and different teams potentially managing them. Infrastructure changes might require stricter reviews than application config updates. It provides better separation of concerns and clearer audit trails.
Okay. And for the modern parts of the environment, Kubernetes clusters especially, how do you ensure the running configuration stays aligned with what's defined in those Git repos?
That's where continuous reconciliation tools come in. The blueprint mentioned tools like Argo CD or Flux. These are core components of a GitOps workflow.
How do they work?
The core principle of GitOps is that Git is the single source of truth for the desired state of your system. A tool like Argo CD runs inside the Kubernetes cluster. It constantly monitors the live state of the cluster, what deployments exist, what service is running, etc., and compares it against the desired state defined in the manifests stored in your Git repository.
And if there's a difference, if someone manually vector edits something.
If drift is detected, if the live state doesn't match the Git state, Argo CD, or Flux, automatically takes action to revert the cluster back to match the desired state defined in Git. It continuously reconciles reality with the declared intent.
Self-healing configuration, effectively. Okay, that works for Kubernetes, but what about those thousands of legacy Windows servers? You can't run Argo CD on them. How do you apply the same desired state management model to classic infrastructure?
You need agents for that. For the legacy Windows estate, the blueprint recommended using configuration management tools running in a pull-based mode, like PowerShell DSC desired state configuration, or maybe Ansible agents configured to pull their configurations from a Git source.
So the agent on the Windows server periodically checks the Git repo for its configuration.
Exactly. It checks its instructions, the desired state, what software should be installed, what registry key should be set, what services should be running, defined in code, and Git compares it to its current state and corrects any drift it finds. This ensures that even those legacy Windows workloads maintain their required security baselines and configurations as defined by code, preventing them from slowly drifting out of compliance after they're initially built or patched, or if someone makes a manual change. Hashtag 4.3 Enterprise Observability and SRE practices.
Right, getting configuration drift under control. Now, observability gathering all that telemetry is the essential fuel for SRE practices. We mentioned OpenTelemetry earlier as the chosen tool for unifying telemetry across this complex dual cloud estate.
Yes, absolutely critical for consistency. Getting traces, metrics, and logs flowing in a standard schema, regardless of whether the service runs in Azure, AWS, Kubernetes, or even on a legacy VM. That unified data feed is the foundation.
But once you have this massive fire hose of telemetry data flowing, how do SRE teams know what actually matters? How do they cut through the noise?
That's where defining standards comes in. The blueprint mandated defining golden dashboards that cover what are often called the 4 golden signals for every single critical product or service.
Okay, let's quickly recap those 4 golden signals for listeners because they're so fundamental to SRE thinking.
Definitely. First is latency. How long does it actually take to serve a request? Usually measured at different percentiles like the 95th or 99th percentile, P95, P99.
Okay.
Second is errors. The rate at which requests are failing, either explicit failures like HTTP 500 errors, or maybe implicit ones like returning wrong data.
How often it breaks.
Third is throughput, the sheer volume of work the system is handling, usually measured in requests per second or transactions per second.
How much work it's doing.
And fourth is saturation, how full or stressed the service is. This is often the trickiest. It's not just CPU utilization. For a database, it might be connection pool usage, replication lag, or disk I/O limits. For a queue, it's the queue depth. It measures how close you are to hitting a resource capacity limit. Tracking these 4 signals gives you a really good high-level picture of the health and performance of any service.
Latency, errors, throughput, saturation. Got it. And this data, these signals, feed directly into the most critical SRE artifact, the service level objectives, or SLOs. The blueprint had a great detailed example for a critical HR payroll application.
Yeah, that was a good concrete example. For a system handling sensitive stuff like salaries and regulatory filings, the SLOs have to be robust and clearly aligned with what the business actually needs. The proposal was something like 99.9% monthly availability for core functions like submitting payroll.
3 nines. Okay.
Rigorous latency targets, too, specifically. P95 latency under 300 milliseconds for read operations, like viewing payslips.
Let's just unpack P95 latency again quickly. What does that mean in practice for the user?
It means that 95% of the time, when a user performs that read operation, the response must come back in under 300 milliseconds.
Mm-hmm.
The slowest 5% of requests can be slower, It's a much stricter and more user-centric measure than just looking at average latency, because averages can easily hide a poor experience for a significant minority of users if you have a few very slow outliers.
Yeah.
P95 gives a better picture of typical worst-case performance.
Right. Focuses on the bulk of the user experience. What else was in that SLO example?
They also set clear DR goals as SLOs. An RPO, recovery point objective, of 15 minutes, meaning the business agreed they could afford to potentially lose up to 15 minutes of data in a disaster. And an RTO, recovery time objective, of less than or equal to 1 hour, meaning the system had to be fully restored and operational within 1 hour of declaring a disaster.
And the crucial step here wasn't just the tech team defining these.
No, absolutely critical. The business stakeholders, in this case, representatives from HR and finance, had to formally review and sign off on these objectives. This ensures the technical targets are aligned with the actual business tolerance for risk and downtime, and that everyone understands the trade-offs involved in achieving or not achieving those levels. It links the tech directly to business impact.
So everyone agrees what good enough looks like. Okay, and the ultimate goal with all this monitoring and SLOs is to drive automation and self-healing.
Right, that's the aim. You want to build intelligent alerts, not just noisy alerts like CPU is high. You want alerts based on multi-signal context, ideally tied to SLO violations, like P99 latency has exceeded the SLO threshold for 5 minutes and the error rate is increasing.
Smarter alerting.
Smarter alerting that routes directly to the team responsible for that service. And even better, wherever it's safe and the failure mode is well understood, those alerts should trigger automated runbooks or remediation actions. Maybe automatically restarting a service, clearing a cache, scaling out instances, addressing known repeatable incidents without needing human intervention in the middle of the night. That's the self-healing aspiration. Hashtag 4.4 advanced automation and DR validation.
That automation extends beyond just alerts, right? The blueprint talked about enterprise runbook automation for all sorts of operational tasks. These need to be pretty robust, I imagine.
They do, and ideally, platform agnostic. They should be written in common scripting languages. PowerShell, Core, Python are good choices so they can run anywhere, and executed by centralized automation services like Azure Automation or AWS Systems Manager Automation, or even Lambda functions.
And key characteristics for these runbooks.
They absolutely must be idempotent, meaning you can run the same script multiple times and it will always result in the same desired state without causing errors or unintended side effects on subsequent runs. That's crucial for safety. And for any runbook that performs sensitive actions, it needs to have documented approval workflows integrated, maybe requiring manager sign-off before execution.
Idempotency and approvals, got it. Now, let's tackle the most advanced and frankly maybe the most intimidating practice mentioned in the whole blueprint, chaos engineering, specifically doing it in a regulated production environment. That sounds risky, not for the faint of heart.
It absolutely requires extreme caution, and the architect was very clear about mandating that caution. This is not about just randomly breaking things in production and hoping for the best.
No chaos monkey let loose on the payroll system on Monday morning.
Definitely not. The approach has to be highly controlled and incremental. You must start small and always start in non-production environments first. You rigorously define the experiment. What are you testing? What's the hypothesis? What's the potential blast radius if something goes wrong? What are the safety boundaries, the hard stop conditions or circuit breakers?
So, very planned experiments.
Very planned. You need full stakeholder buy-in and approval before you run anything, especially as you get closer to production. The goal isn't actually to cause an outage. The goal is to proactively uncover hidden weaknesses, dependencies, or incorrect assumptions in your system's resilience before a real failure happens.
Learn from controlled failure.
Exactly. You use the results, what you learn about how your system behaves under specific failure conditions, like network latency or a dependency failing, to improve your monitoring, your alerting, your automated runbooks, and potentially even the system architecture itself. Only then, once you have confidence from non-prod testing, do you consider very controlled, limited-scope chaos experiments in production, usually during defined maintenance windows, with heightened monitoring and immediate rollback plans.
Can you give a simple example of what a controlled production chaos drill might look like in this regulated environment, maybe for that financial system?
Okay, a relatively safe one might be simulating network degradation between two internal services. You could use a tool to inject, say, 500 milliseconds of extra latency just on the network path between the web front-end service and the back-end authorization microservice. You do this for maybe only 5 minutes during a low traffic period.
And what are you looking to see?
You're looking to see if the front-end service handles this gracefully. Does it have proper timeouts configured? Does it maybe activate a circuit breaker pattern to stop hammering the slow service? Does it return a sensible error message to the user or degrade functionality gracefully, rather than just hanging indefinitely, consuming resources and potentially causing cascading failures? Seeing that successful, graceful failure proves that part of your resilience design actually works as intended under realistic conditions.
Okay, proving resilience through controlled stress. Now, how do you satisfy the auditors? They come knocking, wanting proof that your DR plan works, that you're resilient. They don't just take your word for it, they want hard evidence.
Yeah, auditors need proof. This requires adopting what you might call an evidence as code or continuous compliance mindset. It ties directly into your governance, risk, and compliance GRC processes. You need to be able to produce verifiable evidence on demand.
What kind of evidence?
Things like detailed logs of successful regular backup restore tests, measured RPO and RTO data from those tests, proving you met your targets, configuration exports showing your immutable backup settings are correctly applied, evidence of segregated credentials and JIT access controls, clear documentation of your DR runbooks, and the results of chaos drills. All of this needs to be documented, stored securely, and readily available.
Sounds like a lot of manual work together that every audit cycle.
It can be, which is why the architect mandated automating the generation and collection of this evidence as much as possible. Ideally, integrating it with a GRC tool or packaging it up automatically into an audit package. The goal is to have minimal scramble and manual effort when the auditors arrive. The parts of compliance should be a continuous output of your automated processes.
Okay, let's zoom in on some specific tricky challenges. First, the big one for many companies, transforming those thousands of legacy Hyper-V VMs and classic Windows workloads. This is often the biggest chunk of the migration effort in terms of sheer volume.
It really is. The first step is the technical migration itself. The blueprint recommended using Azure Migrate for its agentless replication capabilities, which simplifies moving Hyper-V VMs. But it's not just flicking a switch. No, it needs careful planning. You need to define cutover waves to migrate applications in logical groups, minimizing risk and validating dependencies. You absolutely need to use tools like Azure Advisor before the migration to right-size the VMs based on their actual performance data, not just their on-prem specs, to avoid overspending in the cloud. And critically, as they land in Azure, they need to be re-architected into the new secure hub-spoke networking model, not just dropped into a flat network.
Okay, lift and shift, but with right sizing and network integration. Now, a key decision point for these Windows workloads once they're targeted for modernization is, do they stay as VMs or can they move to Windows containers? What are the clear decision criteria there?
The main criteria boil down to dependencies and state management. The blueprint suggests using Windows containers primarily for stateless .NET Framework or newer .NET Core microservices or web applications. Workloads that are easily packaged, don't need deep OS access or kernel-level drivers, and can handle being ephemeral.
Okay, stateless, modern-ish apps go to containers. What stays as a VM?
You generally keep workloads as VMs if they require specific custom drivers, maybe for hardware integration that persists even in the cloud. If they need specific OS features or roles not available in container-based images, or if they have tight dependencies on legacy components or third-party software that just isn't container-friendly. Also, stateful applications that haven't been re-architected for distributed state often remain easier to manage as VMs initially. VMs offer that full OS environment, stability, and access to all the OS hooks, which some legacy apps just need.
Got it. Containers for stateless, VMs for stateful or complex dependencies. Now, what at the heart of the Windows legacy world? Active Directory itself. You probably have an old forest, maybe multiple forests. You can't just migrate that whole thing in a big bang, can you?
No, absolutely not. A big bang AD migration is almost guaranteed to cause massive disruption and pain. The recommended strategy is always phased and coexistence-based.
How does that work?
You typically start by establishing cross-forest trusts between your old on-prem AD forest and a new, clean AD forest built following best practices in the cloud or using managed AD services. You set up new domain controllers in the cloud side by side with the old on-prem ones, ensuring replication works. Then you use tools like the Active Directory Migration Tool, ADMT, to migrate users, groups, and computer objects in manageable reversible phases or batches.
So resources in the new cloud environment can use the new AD while legacy stuff still uses the old one, but they trust each other.
Exactly. It allows for gradual migration and ensures business continuity throughout the process. New cloud-native applications can leverage the cleaner, modern AD structure from day one, while legacy applications, depending on the old structure, continue to function via the trusts until they too can be migrated or retired. Hashtag tagged 5.2 M&A integration and governance at scale.
Okay, another classic spanner in the works for any well-laid cloud strategy. Mergers and acquisitions, M&A. Suddenly you inherit a whole other company's IT estate, possibly with its own completely different cloud strategy, or maybe no strategy at all. How does this blueprint approach integrating potentially disparate environments?
M&A integration is tough. The crucial first strategic step recommended here is to build a neutral landing zone.
Neutral, meaning not in either company's existing cloud setup.
Exactly. A separate, clean environment, maybe a new Azure subscription or AWS organization that's initially independent of both the acquiring companies and the acquired company's existing infrastructure. This neutral zone is used to host only the essential shared services needed for integration. Things like centralized DNS resolution between the two environments, maybe the new consolidated PKI infrastructure if needed, centralized logging collectors, and potentially secured network transit routing capabilities. It acts as a stable, common middle ground, decoupled from the complexities and potential conflicts within the merging organization's existing setups.
Okay, build a neutral ground first. Then what?
Then the priorities are usually identity consolidation, getting users from both companies into the primary IDP, enabling collaboration, merging the networks, usually via secure transit routing or private peering established through that neutral zone, and importantly, standardizing the mundane but critical stuff like resource tagging schemes and CMDB data formats so you can actually manage and report on the combined estate coherently.
Makes sense, but the architects stress something really vital operationally here.
Yes. You absolutely must define the day two operating model before you cut over services or fully merge networks.
Where before?
Because the operational surprises that hit after the merger. Who is responsible for patching these newly acquired servers? Who pays the cloud bill for this migrated application? Whose monitoring system is watching this? Who has the admin passwords? Those are the things that cause chaos, service outages, and security incidents. Ownership, monitoring processes, patching cycles, support handoffs.
Yeah.
All that needs to be figured out and agreed upon up front before the technical merge happens.
Avoid the post-merger operational firefight.
Right.
And managing all this complexity, whether from M&A or just organic growth, across a global dual cloud footprint requires really strong, centrally enforced governance, right?
Absolutely essential. You need to enforce global guardrails consistently across both Azure and AWS. And the tools for that are things like Azure Policy and, again, AWS Service Control Policies, SCPs, or maybe AWS config rules.
And what kind of rules are we talking about here? What are these global guardrails enforcing?
They enforce the non-negotiable boundaries. Things like denying the creation of public IP addresses on VMs in any region unless explicitly approved, enforcing mandatory tagging on all resources, tags for cost center, application owner, environment, which is critical for FinOps and management, requiring encryption to be enabled on all sensitive storage types like databases and object storage buckets, blocking the use of specific, unapproved services or regions entirely. These top-level policies set the hard limits that individual teams cannot override.
Setting the boundaries for everyone. And finally, getting back to helping developers move fast but safely within those boundaries. Delivering those standardized, compliant application templates requires more than just code, right? It needs a catalog.
Yes. The platform engineering team can build the greatest golden modules and templates, but if developers can't easily find them, understand how to use them, or see examples, they won't get adopted. The platform team must publish these golden paths, these pre-built, vetted templates for common application stacks.
Like a standard 3-tier web app template.
It's exactly. Maybe a template using VM scale sets, Application Gateway, and Key Vault in Azure, or the equivalent using EC2 auto-scaling, ALB, and Secrets Manager in AWS. These published templates must include not just the infrastructure, but also the built-in identity integration, logging configuration, backup policies, security settings, and crucially estimated cost implications. And all of this needs to be documented clearly and made easily discoverable in a unified internal developer portal or service catalog. Tools like Backstage or even just well-structured internal documentation sites can serve this purpose. It makes compliance easy to consume. Hashtag tag 5.3 cost control tactics.
Okay, let's talk brass tacks. Cost. The ultimate business driver or constraint in almost any large-scale modernization effort is managing the budget. The blueprint apparently had a pretty aggressive mandate, a 25% cloud cost reduction target. What are the main levers you pull to achieve something like that? It sounds huge.
It is aggressive, yeah. It requires a multi-pronged attack on waste and inefficiency. The primary levers usually fall into a few categories. First, basic technical optimization. Right sizing. Using the utilization data gathered maybe in year one to shrink oversized VMs, databases, and storage volumes down to what's actually needed, that's often the biggest quick win.
Stop paying for idle capacity.
Exactly. Second, financial commitment optimization. Moving workloads that have predictable, steady-state usage onto reserved instances or savings plans. These offer significant discounts, often 40–70%, compared to on-demand pricing in exchange for a 1- or 3-year commitment. Identifying candidates for ISSP is key.
Okay, commit for predictable workloads. What else?
Third, leveraging elasticity in different pricing models. Aggressively using spot instances for non-critical, fault-tolerant workloads like batch processing or some types of dev test environments. Spot instances offer massive discounts but can be interrupted, so the workload needs to handle that. And fourth, just plain elimination. Having aggressive tooling and processes to automatically identify and shut down or delete idle resources, forgotten VMs, unattached disks, old snapshots that generate zombie costs without providing any value.
Right sizing, reservations, spot instances, and eliminating waste. Got it. And the framework, the organizational structure that supports all this constant optimization and financial discipline.
That's the robust FinOps program we talked about earlier. This can't just be a once-a-month review of the bill. It needs to be deeply integrated. It involves real-time, or near real-time, visibility into costs, driven by that mandatory tagging. It requires building strong processes for showback, reporting costs back to teams, maybe even chargeback, actually billing teams internally. And critically, mapping that cost accountability directly back to the product teams who own the services.
Making them financially responsible for their architectural choices and consumption.
Yes, when teams see the direct cost impact of deploying an oversized cluster or leaving test environments running over the weekend, their behavior starts to change. FinOps provides the visibility and accountability needed to drive that cultural shift towards cost consciousness.
Okay, one final point that bridges security and cost. That tricky balance of preventing data exfiltration, massive unwanted data egress, while still allowing legitimate internet access for updates, APIs, etc. How do you control egress securely without breaking everything or racking up huge firewall costs?
That is a delicate balancing act. The strategy outlined in the blueprint focuses on centralization and inspection. You centralize all outbound internet traffic from your workloads through a dedicated egress point, typically a managed firewall service or a cluster of network virtual appliances, NVAs, sitting in your hub, VNet, or transit VPC.
So nothing gets out directly.
Ideally, no direct internet access from workload subnets. Everything routes through the central injection point. This allows you to apply consistent, detailed security policies, URL filtering to block access to malicious or unwanted sites, DNS filtering, intrusion prevention systems, IPS.
Okay, central inspection. What else?
Combine that with heavily promoting the use of private endpoints for accessing PANOS and even supported SaaS services. If your application needs to talk to Snowflake or Salesforce or Azure DevOps, can it do that over private link private endpoint instead of going out to their public IPs? This keeps traffic off the public internet entirely for those services, enhancing security and sometimes reducing egress costs. And finally, you have to heavily monitor those egress flows, even the inspected ones, using network flow logs, firewall logs, and again, UEBA, to look for anomalous patterns that might indicate data exfiltration attempts bypassing your filters. It's layers again. Hashtag tag outro.
Wow. Okay, that was incredibly dense, but really, really practical. The enterprise cloud modernization blueprint we've unpacked today really does feel like a masterclass in managing complexity at scale. It's such a powerful mix of specific technical tactics, things like insisting on immutable backups, adopting OpenTelemetry universally, mandating private link for PARIS.
Yeah, the technical specifics are crucial, but it's equally, maybe even more, about the massive procedural and organizational shifts that have to happen alongside them.
Right. That's the real transformation, isn't it? The shift away from traditional siloed IT towards becoming a more agile, product-focused organization driven by those SRE principles of SLOs and error budgets.
Absolutely. And we saw that really clear emphasis on building stability first in year one, getting zero trust basics in place, securing the data with immutability before the organization gets permission, effectively, to chase the more advanced optimization in year three through things like deeper automation and serverless. Success really seems to hinge on implementing governance through code, automating compliance, and enforcing clear automated accountability for reliability and cost.
Absolutely. It really hammers home that successful modernization at this level is as much about the the governance, the automation, and the operating model as it is about the specific cloud technologies you choose. And that target operating model we discussed, it really requires deeply integrating three core high-value disciplines that maybe weren't central to IT a decade ago: FinOps, SRE, and platform engineering.
Yeah, this blueprint makes a strong case that neglecting or underinvesting in any one of those three core pillars, FinOps for cost control, SRE for reliability, platform engineering for developer velocity and standardization, will pretty much guarantee either architectural failure or financial chaos, especially in
Wow.
a complex, large-scale dual cloud world. They're interdependent.
Okay, so to wrap up, we want to leave you, our listener, with a final, maybe provocative thought to chew on, building directly on that need for these new disciplines, thinking about your own organization, your own context. Of those three critical functions, FinOps, SRE, or platform engineering, which one do you think will deliver the most critical, needle-moving business value for the specific challenges you face in the next 12 months? Where should your immediate focus and investment perhaps go first to break through your current modernization bottleneck? Something to think about.